Hey there, folks. Back here with another video in our study of what is going to be our first application, mathematical application of the limit. This idea known as the derivative. We had looked at last time just a little application of the derivative, or we might say here interpretation of the derivative. We opened with that classical problem in calculus known as the slope of the tangent line problem. And we looked at a technique for developing a solution to that problem. And what we were looking at in that technique, folks, what we performed in that technique was what's known as a derivative calculation. All right. So what we're going to do today is come back and introduce the derivative. All right. So you'll see this is where my notes open, right, with this set. Where I begin by just taking note here that, yes, the tangent line problem, right, is answered using a process of calculating what is called the derivative of a point, right? Careful there. The derivative at a point for a function, right? When we solve the slope of the tangent line problem, we are solving that problem with a calculation that is known as calculating the derivative at a point for a function. And if we go back and recall here, what we mean by that, right, is this calculation seen here. All right. By definition, derivative at a point, right, is defined as for the function y equals f of x, the derivative of f at x equal to a, is this value we denote, first of all, as f prime of a. And as for its calculation, it's equal to a limit evaluation, right? It's equal to this limit evaluation where we take the quantity f of a plus h minus f of a and divide by this value of h being the argument of the limit, right? H being the variable of the limit, right? The variable of interest in the functional expression, right, described by this ratio. And if we remember, this ratio is just looking at change in rise, right, the vertical change in the output of a function over a sequence of x that has h units of length, where then h, again, is that horizontal change in x. And when we look at the behavior of that, what we think of as back in the slope of the tangent line problem, the slope of the secant line, it gives us that slope of the tangent line, or what we would call, in general, the derivative of f at the coordinate x equal to a, right? Or at the value, the independent variable value at x equal to a. Right? It would be at the coordinate a comma f at a. Right? And when we perform this calculation, its interpretation, right, to give ourselves a little bit of useful interpretation here, is it is interpreted as indeed what we used it for in the opening, and that is this calculation of slope of the tangent line for a function at a value of x, right, at a value of the independent variable in the function, right, at a specific value of x equal to a. Right. Let's, I believe, at another example here. We can just run through this calculation. Here's another function, right? Here's a specific case where f of x in this case is equal to the quantity x plus 2 cubed. And we're interested in finding what we call the derivative of f at x equal to 3. We might say we're interested in finding what's the slope of the line tangent to this cube function at the value of x equal to 3. Now we can certainly see when x is 3, we have 3 plus 2 And that gives us 5, and 5 cubed is 125. But that 125 is just the output of the function at the value of 3. Right? What we are interested in is what's the slope of the line tangent to the curve at that coordinate 3, 125, 3, f at 3. Well, that slope of the tangent line, that derivative of f at 3, is given by f prime at 3, the value of f prime of 3. And it's the limit calculation above where we substitute in for the value of a here. We can see we get substitute in for it the value of 3, which gets substituted in here and here into the calculation. Right? And as we noted, that's going to describe the slope of the tangent line for function f at the value of 3. Right? So substituting it in, we produce this result, all divided by h, where we've stated what f of 3 is. We know f of 3 is going to be 125. Right? As for f of 3 plus h, we are just going to plug 3 plus h into the function above for the value of x, which does simplify the statement inside the group into 5 plus h being cubed. And if we cube 5 plus h, that does cube to give us 125 plus 75h plus 15h squared plus h cubed. Now, if we take away from that in quantity the value of f of 3, as we see in the numerator, this expression here, that will live behind just these last 3 terms involving the value of h. So if we think about this in the limit, right, and we take away that 125 in the first step, that is going to leave just behind those 3 terms involving the value of h, where when we divide out an h from each of those 3 terms, it leaves behind just this quadratic function. Where we know how to evaluate now the limit of that quadratic by substitution, and we can see the slope of the line tangent to the curve at that location is going to be equal to the value of the limit, which is the value of 75. Let me move my arrow from the screen there, and you can see that result. All right, so that is f prime at 3, right? The slope of the line tangent to the curve of f at 3, right? Slope of the line tangent to the curve x plus 2 quantity cubed at the value of x equal to 3 is f prime of 3 equal to 75. Right? The derivative of function f, this function here, at the value of x equal to 3 was calculated by definition, this value of 75, right? And maybe we should highlight that. This is thus, by definition, right? What we are going to point out here, and maybe I should point that out while I make this statement and make this little change, is that we're not always going to use the derivative or the definition to calculate the derivative. What the definition of the derivative is going to give us is a way to look at functional types in general and develop a set of rules for those different function types where we can, in the future, when calculating our derivatives, rely on a set of derivative rules. The last thing we're going to want to have to do is perform this calculation, right, for this limit with this simplification involved in the argument, right, for every single function type. This does happen conveniently, we see here, for polynomial functions and perhaps even for cases of like rational functions. But when we start to look at trigonometric and exponential functions, things are going to get a little trickier. And when we start to look at complex combinations of functions, well, yes, most certainly we're going to want to be able to rely on a set of rules versus rely on this, what could become a complex calculation. All right. Now, we were calculating at the derivative of f at a very specific point. What we should point out is that you can ignore the calculation at a very specific point, or in a sense generalize it to be at any point, right? And develop what is known as just the function's derivative calculation. And develop what's called the derivative function for a given function, right? What I say here is the derivative calculation for y equals f of x at x equal to a can be generalized for all values of x in f's domain to determine what's called the derivative function for f. Right? This process is known as differentiating the function and is defined as follows. Right? We call this the process of differentiation for any given function. And it is this calculation we've seen above for the derivative of the function at a particular value of x, except we don't consider that x at that value. You can see this calculation looks a lot like what we've defined above, right? Except you can see here we have not specified it for a particular value of x equal to a. We have stated it in general just for the value of x. And that's what's unique about this calculation, is that x, where we replaced it with the value of a in the previous example, is not a limit calculation that depends upon that value of x. It's a limit calculation that depends upon this horizontal distance h. So we can generalize it to any given value of x, as we see done here in this definition. Right? Note, y equal to f prime of x denotes a functional relationship related to f instead of a slope of a tangent line at a particular value of x equal to a in f's domain. Right? It's a function that describes that slope at every given value of x. It's what we might call a slope function. Right? It takes as input a location in f's domain and gives as output the slope of the line tangent to the function f at that location. And additionally, it has some other notation involved. We do see a variety of notation used to talk about this value f prime of x, right? And that is for y equals f of x, we can write that as f prime of x being the derivative of f at x. We can write it as y prime, right? And this does make use of what we call prime notation. If we see a function f followed by the prime notation, it is referring to the derivative of that function f. And we can apply that prime notation not only to f, since y equals f of x, we can also apply it to y. And we can see it defined as y prime, right? The first derivative of y, which equals this function f of x, right? Another notation, this is the first bit here is denoted as prime notation. The rest of this notation is referred to as, well, these other two pieces I highlight here are referred to as Leibniz notation, Lebniz notation. Leibniz, named after the mathematician Leibniz. Right? Leibniz was had a big influence on the notation of calculus, where some might say calculus was discovered by Newton being the father of calculus. Leibniz was right there along with Newton in his exploration of the topic, and was actually very fundamental in developing calculus as we understand it today, including the notation. All right. So this is referred to as Leibniz notation. This is the notation he used. And this is a common way to denote derivative of a function. Right. This says I want to find the derivative of the value y with respect to x. Right. We might say this notation is taking, and I could maybe denote it this way. We have our value y, and we're taking the derivative with respect to x for our function, our value of y. We're applying this operator d dx. We call this the operator for the differential with respect to x to this value of y when we talk about dy dx. We can also think of it being applied to function f of x if y is equal to f of x in our notation, right? So we can think about having function f of x where we then can apply by wrapping it with the derivative operator d dx, which indicates that, again, the first derivative, or we're going to find called the first derivative, or the derivative of f with respect to x. Right? And then this last notation is a bit of more less common notation. It is called big D operator, right? We can think of that as big D being the capital D being the operator for the derivative, where we're seeing here it being applied to function f at x. And what we do see applied to the differential operator in this notation is little subscript x, which is indicating the variable of the differential. Right? The variable of the derivative, of the differentiation, I should say. Right? So this is just a little bit on notation. We do see that f prime of x in the definition denoted using several different notations. We can see it to begin with denoted using prime notation on both f and y, but we can also denote it using Leibniz notation or with this capital D notation. All right? I'm going to take a quick break here, and I'll be right back. All right. Well, hopefully you took a moment to take that in, that definition. That definition right here that's up on the board, folks, is a crucial definition in the coming sections. It is going to be the way that we're going to go for any function here, right? For any function, be able to develop a formulation for its derivative. To be able to develop a formulation by using this calculation on this function type. This function type not being only polynomial, but being the case for rational, being the case for exponential and logarithmic and trigonometric, right? All those cases can have a formulation developed for their type of function where we can calculate that derivative with that what we might call rule, right? Versus having to always rely on this limit value. Right? So, yeah, this is a really important definition and why we are spending this bit of time on it, right? So take note. I do run through a calculation with this, right? I do just consider the square function, right? That's probably the simplest of our polynomial functions that are beyond linear, right? We're going to see here. But if we consider f of x equals to x squared, and notice, why would we not want to look at a linear is, keep in mind this, well, we are going to look at a linear, but it's not very unique. A linear function's derivative behavior. Remember, it tells us slope of the tangent line, and linear functions have tangent lines that are given by the function themselves. So their slope of the tangent line really becomes the slope of the line themselves, and are constant in their behavior. It's not until we add a little curvature or some curvatures, some curves to our function behavior that we start to see some varying of the slopes tangent to those curves. Next simplest being up from linear, being just a simple bend, that being the square function, right? The curve given by the square function. Right? Well, we know the slope of the line tangent to the curve will all be described by this calculation here from the definition above for f prime of x. Right? If f of x is x squared, then f of x plus h will be x plus h quantity squared, and we can expand that out. X plus h times x plus h is x squared plus 2xh plus h squared. Right? Simple FOIL will expand that out. So if we set up our f prime of x calculation using the definition above, and we subtract x squared from x squared plus 2xh plus h squared, we will see that x squared term remove itself with this difference. And we'll be left with 2xh minus h squared, where that common factor of h in each of those terms can be divided out with that h in the denominator, leaving us with 2x minus h, where now if we evaluate the limit of this statement here, which does, yes, have two variables, x and h, the limit is only interested in the behavior of h alone. The limit as h heads to 0. So if we consider evaluating this using substitution, just substituting in for that value of h, the value is 0, and maybe I should illustrate that step here. Since this is kind of new to us, this is going to be 2x minus 0, right? This is all going to end up with the result of 2x in the end, right? Thus, the derivative of the square function is the linear function 2 times x. Right? The derivative of f of x equal to x squared is given by f prime of x equal to 2x. Right? And what we want to remember is f prime of x, this function 2x, describes all of the slopes tangent to the curve x squared at every single point along the curve. Right? At every single value of x from negative to positive infinity, we can describe the slope of the line tangent to x squared by using the function f prime of x equal to 2 times x. Right? At any value of x, the slope of the tangent line will be twice that x, is what f prime of x is telling us. Right? We can actually see this illustrated if we were to graph these two functions side by side. Right? You can see here's the graph of f of x, and what we're interested in is looking at different points along f, and what is the slope of the tangent line at those points. Like, what's the slope of the tangent line here at x equal to negative 2? Well, certainly it would be negative in value. And the way we would see that is if we go over and look at the graph of f prime of x, we can see that f prime of x at negative 2 is indeed the value negative 4. It is 2 times that negative 2 in value. It's this location seen right here on our graph. And it is below the x-axis in the graph of f prime. It is negative in value, illustrating that negative slope. And as this graph illustrates over here for f prime of x, we expect negative slopes on the graph of the parabola x squared for all values of x, starting way down here at negative infinity and moving all the way up towards and equaling the, well, up to the value of 0, but not equaling it. We can see that would be the behavior on the left half of this parabola. All the slopes tangent to the curve would all be negative, starting rather steep at a very small negative number down here at towards negative infinity, but as they move in closer to 0, getting less and less steep, becoming more and more level. Where at the value of x equal to 0, we can see what happens is the slope of the line tangent to the curve here is illustrated to be 0. And then for values greater than 0, all the slopes would become positive, starting very close to level, but becoming more and more steep in the positive direction as we move further down the x-axis. And that is all that's being illustrated on the graph here for the function 2x. Right? And this is all summarized below in this summary here. Right? Notice the behavior of the slopes for the tangent lines, f of x prime of x, right, is linear. Right? Where when x is less than 0, f prime of x will be less than 0, and the slopes will be negative. And when x is greater than 0, f prime of x will be greater than 0, and the slopes are positive. Notice this behavior is linear for f prime of x, and when you're less than 0, you will have negative slopes on this graph. And when you're greater than 0, you'll have positive slopes. And also when x equals 0, right, your slope will be nothing. It'll be 0. All right? That's all illustrated here in the graph of f prime of x. To help highlight this, I also have another illustration of this. Let me bring this up. Here is illustrating the same concept. This function is slightly different. This is 1/4 x squared versus just x squared. But it gives us this parabolic shape and the corresponding slope of the derivative function, right? The slope of the tangent line. The parabolic shape seen here, can I actually highlight it? Let me bring that up. I'm sorry. For the parabolic function seen here, right, we're interested in the slope of the tangent line. Now this demo is uploading again. Nope, I got to replot it. Give me a second to let this load. Actually, let me pause this for just a moment. We'll see if we can get this to load a little quicker. It's going to take a minute. All right, folks, I think I'm back here. I got it figured out. And if I was to flip back, again, what I want to illustrate is what's going on in this static illustration here, these two static illustrations. I want to show you what is actually trying to be illustrated here. And the way I have to do that is with this manipulative I've put together over on Wolfram Cloud. And what this manipulative shows, I actually adjusted it here so it actually shows the illustration that's in your notes. Right, here's the square function in blue, x squared, and here is its derivative function 2x in the illustration. All right, we can see here's the function in blue that's given by x squared, and here is our derivative function 2x in yellow, if you can see those colors, right? And this is a little manipulative where I can change the values of x. You can see that up here at the top. So I can grab this slider bar and I can start to adjust my values of x. And you can see as I move my values of x, I have 2 points on the graphs that also change with respect to that x and align themselves along the x-axis with respect to the x value that we're at. And in fact, maybe I should turn that on. Let's turn on the value of, well, you can see there that it does correspond to that value of x. Maybe we don't want to have that on at the moment. It does take up a little bit of vertical space. All right, but we can see we're going to be at that particular value of x right there. I think that was like negative 2.34 or something like that. So as I scroll forward, what you will see is that value of x change. We're next to the blue line, right, the graph of x squared. I've also graphed at that location of x the tangent line, whose slope is being described by this yellowish orange line, right? And as we can see at this exact value of x, the slope of that line is negative, and it does illustrate a negative slope. And as long as I stay on the left side of this graph, right, as I move my slope back and forth, that slope will always be negative, as illustrated down here in my graph. Now, the closer I get to 0, you can see the closer the slope gets to being nothing in value. To where at the point where we're right around an x value of 0, the slope of the line tangent to our curve would also be the value of 0. Now, where are we at in this animation? We're about negative 0.1. So, I mean, I could put us right at 0 here. Oh, that's going to jump by ones. So I can just put us right at 0. Right? And you can see you can't even see that tangent line because it is lying right on top of the x-axis in this illustration. And as I move forward into the positive region, right? You can see my slope is now going to become positive, tangent to this curve of x squared. And that's going to be being illustrated with the output seen along the orange graph in our illustration here. Right? Let me go back up here and minimize this. Come back down, scroll back to this illustration. Or I can just kind of scroll if it'll line up. So you can see here as I scroll to the right, I see nothing but positive slopes over here for values of x greater than 0. And that's being highlighted there on the orange graph, right, at those corresponding locations. So this little manipulative here that I'm changing the values of x in is illustrating, I hope, the static information being given in this table seen here, or in this graphic seen here. The slope of the lines tangent to the curves are illustrated at locations along this curve for f prime of x, where we see negative slopes when we're less than 0 for x, and positive slopes when we're greater than 0, and the value is 0 itself at 0. All right. This graph is highlighting the slopes tangent to the curve seen in this graph. All right. Now, to finish with, we do notice something similar also there to finish with. But what I want to just take note on is that the derivative function is itself also a function. So as a function itself, you can also take its derivative. You can take derivatives of derivatives. And when you take derivatives of derivatives, right, you find what's called a higher order derivative. And if you take the derivative of a function and then you take the derivative again, you find what's called the second order derivative. The first derivative is what's called the first order derivative. The second order derivative would be called the second order derivative, and so forth. Third derivative would be a third order derivative. And these become what we call higher order derivatives. Derivatives of functions are functions, and functions, we can find derivatives for them. So finding a derivative of a derivative is just a higher derivative of the previous. So we do have what's called higher order derivatives, and we do have some notation that goes along with that, that idea. All right. I think I define what are just called second order derivatives, right, and their notation. Right. For y equals f of x, if y prime, or this is all denotes the first order derivative of f, then the second order derivative is going to be given by taking the derivative applied again, right, 2 times to our function f of x, which is like applying this operator in a squared manner. So what we will see is the square of this operator. Right? It's almost as if we have function f of x, and we are wrapping it with the derivative operator squared. Right? That derivative operator being applied twice to our function. Right? We don't traditionally see this middle notation there. I just express it that way to help you understand what we're saying here with this middle formulation. Right? This middle equation. But also, what we get back to is just some notation. The way we denote that second derivative is we use double primes. Right? We can use double primes on y or f, or when we think about applying it in a Leibniz situation, we can think of the second derivative of f with respect to x as illustrated for f of x above, also with respect to y, illustrated as seen here. And this idea does extend into similarly notation for third order derivatives. Right? For a third order derivative, it's like finding the derivative of a second order derivative. So it's like applying the operator again to what we see as a statement like this here, which is like finding a triple prime of y, or a triple prime of f, or the third derivative of our function f of x. right? We could even adopt this notation, which is what I think I'm missing from all that. So maybe we say, instead of that being to the second, we would say that's to the third power in its operation. Right? That is what we call third order derivatives and higher order derivative notation. It just signifies performing this derivative calculation, this limit as h heads to 0 for f of x plus h minus f of x divided by h, applied to not just f anymore, but being applied to f prime and then f double prime and then f triple prime, because the results every time are just going to be different functional behaviors. I do think I note that again for x squared, where we understand f prime of x is 2x. If we apply that derivative operator to f prime, well, that's just like applying this limit now to function f prime of x, which through the work we will see will simplify itself down into the value of 2 in our calculation. All right. Is that where I finish? Thus, I think I do have a thus statement. Yeah. Thus, for our function f of x equal to x squared, the first derivative of f, right, denoted as f prime, is 2x, as seen here. This is f prime of x is equal to 2x, and the second derivative is f double prime of x equal to 2. Right? Where the slope of f, the slope of x squared, is described by 2x, and the slope of f prime is described by f double prime. It's described by 2. And again, if we go back and look at the illustration of f prime, that does make sense. 2x is a linear function with a constant slope of 2. So what would describe the slope of the lines tangent to the curve? Well, they're all going to be constantly the value of 2, which the second derivative tells us. All right? This is higher order derivatives, folks. We can apply, sorry about that. We can apply this definition, right, to the derivative function itself and find a higher order derivative. Right? And this operation, this limit calculation, by definition, is what's known as the derivative of a function calculation. All right? It's what we've defined back here as the derivative function. All right? For y equals some function, f of x, the derivative of f is always just given by this limit operation. And what you end up with is a function whose description describes the slopes of the lines tangent to f itself. All right? Where we're heading, folks, is we're going to be using that derivative function in every formulation, just about, I should say, every rule that we're going to develop for our different function types that are going to become known as our derivative rules. What we're not going to want to do is apply that definition every time we're asked to find the derivative. This definition, the way we're going to use it is we're going to apply it to prove a set of rules that we can then use that set of rules in our calculation of derivatives. All right? Having to always apply the limit can get tricky, right? Can get tricky if that's all we want to rely upon. So what we use it more like is a method to develop a set of rules where we're going to use that set of rules. All right? And that's what's coming in the next set of videos, is we're going to start to develop those sets of rules, right? For all of our different function types, from fundamental cases that involve polynomials to more complex situations, right, that develop through the trigonometric and exponential and logarithmic functions. All right. So that I'm going to break that down into the next sets of videos, folks. So look for those. And that's where we're going to continue with all this. So with that said, I'll end there, and I'll see y'all next time.